Bismillahirrahmanirrahim. Hello and welcome to this recording. And this I am recording for the students of Arab Open University M131 course. In this recording, I am just going to discuss two topics over here, which is related to set operations and matrices. In the set operations, we are going to discuss the identities and how to solve those identities or how to prove those identities, and then we'll move ahead for the matrices. So here we did already discuss in our previous session about the sets and some operations of this set. So this is why I'm going to skip all these about the sets and some operations of this set, and inshallah we are going to study or discuss from here. Now here we are going to see some of the set identities. Those are given here. The first is an identity which is any set union with a null is set itself, and any set intersection with the universal set is a set itself. Then second identity is a domination, which is a set union with the universal set is a universal set, and a set intersection with null is null only, because there is no common element in the null. Idempotent, a set union with a set is set itself, and a set intersection with a set is the set itself. Double complement, a complement to the complement is a, or a set its complement and its complement is a itself. A union B is equal to B union A, and A intersection B is B intersection A is a commutative law. Associative says A union of B union C is A union B of union C, and A intersection of B intersection C is A intersection B intersection C. Distribution says A union with B intersection C is A union B intersection A union C. So it is A union B intersection A union C. In the same fashion, A intersection with B union C is equal to A intersection B union A intersection C. Then De Morgan's law says A union B whole complement is equal to A complement intersection B complement, and A intersection B whole complement is equal to A complement union B complement. Proving these set identities, we can prove by three different methods. One is by equality method. So we'll take the left hand side and we try to reach to the right hand side. It's the left hand side statement we'll take and we try to reach to the right hand side. The second method is use the set builder notation and logical equivalence. The third is using the set identities itself to prove the set identity. Let us do one example for each method. The first we'll take the De Morgan's law. A intersection B whole complement is equal to A complement union B complement. Now we try to prove this by the equality method. We'll take the left hand side and try to reach to right hand side. Now let's assume that a element X belongs to this set A intersection B whole complement. Now if an element is belonging to some complement, then that element is not belonging to that set. For example, if X is equal to 1, 2, X belongs to the set 1, 2, okay, let us then X does not belongs to this set 1, 2. So we say that if this set is A complement, if X belongs to A complement, then X does not belong to A. Okay, A is, for example, it's not 1 2, sorry, it is, let's say, 3 4. Okay, A complement is 1 2. So here it means that if X belongs to A intersection B whole complement, then X does not belongs to A intersection B by the definition of complement. Then it does not belongs to, it means there is no X belongs to A intersection B. So we write this as not of X belongs to A intersection B. Now not of X A intersection B belongs to A intersection B means A intersection B is nothing but the common elements between A and B. It means that X should be present in A and X should be present in B. So we divide this by the definition of intersection as X belongs to A and X belongs to B. So we write X belongs to A and X belongs to B, and we bring this knot over here as whole. Okay, the whole expression, to the whole expression, we bring the knot to the whole expression. So it is knot of X belongs to A and X belongs to B. So we bring this knot inside this expression. It is something like this knot of P, I'm sorry, it is we are over here. So it is something like this knot of P and Q. It is not P or not Q. It is equal to not P or not Q. So we'll take knot inside knot of X belongs to A or knot of X belongs to B. So knot of X belongs to A, it means X is not belongs to A, and knot of X Y belongs to, it means X not belongs to B by the definition of negation. If X does not belongs to A, then X belongs to A intersection, I'm sorry, A complement. And if X does not belongs to B, it means X belongs to B complement. That, or it means a union, and from both the sets, element from the both set, then it is something union. So we write X belongs to A complement union B complement, which is the right hand side. So we started from assuming an element from the left hand side and we reached to the right hand side, hence it is proved. We can prove by another method by using set builder notation. Let us take this identity A intersection B whole complement is equal to A complement union B complement. Assume that A intersection B whole complement is X such that X does not belongs to A intersection B. Again the same thing, if X is in A intersection B complement, then X does not belongs to A intersection B. It means that knot of X belongs to A intersection B, which means X belongs to A and X belongs to B from this one, and knot comes as it is. Then if you bring this knot inside, then knot of X belongs to A, or the AND will become or, knot of X belongs to B. It is again the same thing, P and Q, knot of P and Q, which is equal to not P or not Q. Okay. Then if knot of X belongs to A, it means X does not belongs to A, and or X does not belongs to B. If X does not belongs to A, then X belongs to A complement and X belongs to B complement, or X belongs to B complement. It means that X belongs to A complement union B complement, because it is an OR condition, or it means union. So X belongs to A complement union B complement, and hence we reach the right hand side. So we started from the left hand side and we reach the right hand side, hence it is proved. The third method is by using the set identities itself. For example, let's take this equation A union B intersection C is C in whole complement. A union B intersection C whole complement is equal to C complement union B complement intersection A complement. How to prove this one? First let us remove the complement Okay, by De Morgan's law. If you remove the complement, the union becomes the intersection according to De Morgan's law. So it says A complement intersection B intersection C whole complement. Okay, this has one element and this has another element. Okay, then if you remove from this one the whole complement, then it becomes B complement union C complement. So intersection will become union and the complement is distributed. Now this one, if you take this on this side and this one on this side, it is same again, B union B complement union C complement intersection A complement. Now according to commutative law, B union C is nothing is equal to C union B. So we write C complement union B complement intersection A complement. We reach the right hand side. Okay, so we started from the left hand side and we reached the right hand side, hence it is proved. So these are three methods by which you can prove the set identities. You have another example, you can study this on your own. We'll move ahead for the computer representation of sets. How the sets are represented in a computer. Here we will take an example. Let us take a universal set of 10 digits 1 to 10, and if you want to, this is a universal set, sorry, this is an universal set inside the computer. Now let us say there is a subset called A which the value 13569. If you want to represent this set A inside the computer, then what we have to do is, in the place of element which is present, okay, which is related to it has related with the union, okay, we mark in that place as 1, and the element which is not present we mark that place as 0. For example, here 1 is present, so in the place of 1 we mark as 1. 2 is not there, in the place of 2 we mark 0. 3 is there, we mark 1. 4 is not there, 0. 5 is there, 1. 6 there, 1. 7 is not there, 0. 8 not there, 0. 10, 9 is there, we place it 1, and 10 is not there, we place 0. So in this fashion we place the bit strings in computer for the sets. Moving ahead, the next topic is matrices. So before going to the matrices, just a summary of sets and set operations. So in the set, what we discussed in our previous session and today's session is, we started from the set, what is a set, then we have seen the subset, proper subset, finite set, infinite set, and we have also seen some of the set operations like union, intersection, okay, complement, the set complement, okay, how to make the set complement, and we also seen the Venn diagram, how to draw a Venn diagram for a set, and the important thing we have seen the set builder notation, how to write for any set, for any given set, a set builder notations. Then we have seen some of the set identities, and we have seen three methods of proving the set identities, and we have seen the computer representation of the set. After this we will move to the matrices. Now first we will see what is a matrix. Matrices is a plural of matrix. What is a matrix? Is nothing but a rectangular array of some size or of some objects or numbers arranged in m horizontal rows and n vertical columns, arranged in rows and columns. So how it will look like a matrix? It is something like this, which has some rows and some columns, okay, and every row, intersection of the row and column has an element. For example, this one, first row first column has an element, let's say 1. First row second column has element, let's say 2. First row third column has 3. Second row first column, let's say there is element 4. 5. Second row second column 6. Second row third column. Third row first column 7. Third row second column 8. Third row third column 9. This is called a matrix of m rows and n columns. So how many rows are there? There are 3. And how many columns are there? 3. So we say matrix of 3 cross 3. 3 cross 3 matrix. Now any matrix is called as a square matrix if their rows and columns are same. A number of rows and number of columns are same, then we call that matrix as a square matrix. For example, here 2 cross 2, so it is 2 rows and 2 columns, then we say this is a square matrix. Whereas this one we have 3 rows 2 columns, then it is not a square matrix. Okay. Moving ahead, matrix equality. We can say two matrices are equal if they have same number of rows, same number of columns, and their corresponding elements should be same. Corresponding element should be same. For example, let us take two matrices. One is 1, 2, 3, 4. Another is 1, 2, 3, 4. So we say that these two matrices are equal. Why? Because it has 2 rows and 2 columns, and this has 2 rows and 2 columns, and their elements, the first element are same, second element same, third is same, fourth is same. The corresponding elements are same. Then we say that these two matrices are equal. If this is not, then the matrices are not equal, as given in this example. This is not equal because it just have 2 columns and it has 3 columns. Even the rows it has 2, but the columns are the first matrix 2 and it has 3. Then we say these two matrices are not equal. The order of the rows and columns in the matrix are given. It started from 1 to the mn. Mn is the last element of the matrix. So for example, if the matrix is 2 cross 2, then m is 2 and n is 2. So here the general is given over here. A is equal to array of ij, in which the elements are a11. It means first row, first column, first row, second column. It goes first row, the last column, nth column. In the same fashion, second row, first column, and it goes m row, that is the last row, first column, last row, second column, and the last row, last column. This is how the order of rows and columns comes in a matrix. Moving ahead, the sum of matrices are the addition of their corresponding elements. Now there is a condition for to add two matrices, is that both matrices should have same number of columns, same number of rows. For example, these two matrices has 3 columns and 2 rows. Then we can add these two matrices. How to add? You should add their corresponding elements. For example, 2 plus 7, 9. 6 minus 5, 1. 0 plus 4, 4. Minus 8 minus 1, minus 9. 1 plus 3, 4. 2 plus 6, 8. So you have to add the corresponding elements. Then product of matrix. Product of matrix is nothing but multiplication of two matrices. Multiplication of two matrices. What is the condition here to multiply two matrices is the first matrix column should be equal to the second matrix rows. First matrix column should be equal to the second matrix rows. For example, over here, if you take this example, the number of columns in the first matrix is 3, the number of rows in the second matrix is 3. No matter the number of rows in the first matrix and number of columns in the second matrix does not matter. Okay, so here number of columns of the first matrix and number of rows of the second matrix should be equal. Now how to do the multiplication is the first row of the first matrix is multiplied by the first row of the first column, and it is added to give the first element. Okay, sum of the products of first row, first column, first row of the first matrix and first row of the first column of the second matrix. So here, for example, let us take this one. 0, first we multiply first row, first column to get the first element. So it is 0 into 0, 0 into 0, plus 1 into 2, 1 into 2, plus minus 1 into minus 1, it is minus 1. So you add all this, it is 0 plus 2 minus 1, it is 1. So first the element is 1. Moving ahead for the second, first row, second column will give the second element of the first row. So here you add 0 into minus 1 is 0, 1 into 0 is 0, plus minus 1 into 0 is 0, it is 0. Okay, then first row third column will give the third element. So 0 into 1 0, plus 1 into minus 2 plus minus 1 into 3 minus 3. So it is minus 2 minus 3 plus 0, it is minus 5, or it is minus 5. And the last element, first row last column, it is 0, 0 into 0 0, plus 1 into 0 0, plus 1 into minus 1 minus 1. So the result is minus 1, the last element. In the same fashion for the second row first column. So it is 2 into 0 0, plus 0 into 2 0, plus 3 1 into 1 3. So result is 3. Then second row second column. So it is minus 1 into 2 minus 2, plus 0 plus 0, it is minus 2. Okay, then second row third column, it is 2 plus 0 plus 3 3s are 9, it is 11. So 11 over here. Then second row fourth column, 0 plus 0 plus 3, it is 3 over here. This is the resultant matrix. The resultant matrix, we have number of rows from the first column, number of rows from the first matrix, number of columns from the second matrix. And the condition to multiply is number of columns of the first matrix should be equal to number of rows of the second matrix. The next is identity matrix. Any matrix whose diagonal elements are 1 and the rest of the elements are 0, we call that as an identity matrix. For example, 1 0 0 1. If you see the diagonal element, this is called diagonal element. If it is 1, rest are 0, then we say that it is an identity matrix. Or for example, 1 0 0 0 1 0 0 0 1, then we say this is an diagonal elements, we say this is an identity matrix. Then powers of matrix, for example, a matrix power 1, matrix power 2, it is something like n square, n cube, n to the power of 4. So what you will do, n square, n into n, or n cube, you will do n into n into n. The same fashion you multiply the matrices. Okay, for example, the matrix to the power of 3, this matrix to the power of 3. So what you will do here, they multiply the matrix 3 times. Multiply the matrix 3 times. So first you multiply the first two matrix, you will get this result. Multiply with the third matrix, you will get the final result. Moving ahead, the transposition of the matrix is any matrix, the transposition is the rows are converted into columns, or the columns of the matrix is converted into the rows. For example, over here there are two rows. Okay, these two rows are converted into column. The first row is converted into first column, 2 1 3 2 1 3. Second row, 0 minus 1 minus 2 0 2 1 minus 2. Then this is called transposition of A. Okay, and we write this A power T. Okay. Symmetric matrix is nothing but any matrix is said to be symmetric if the matrix is equal to its transposition. Okay, for example, over here, if you say this one 1 1 1, number of rows, if you convert into number of columns, then the matrix will be 1 1 1 and then 1 1 1. So this is not a transposition. Okay, so here the transposition matrix is this one. Okay, if you convert this minus 2 1 3 into the column minus 2 1 3, then 1 0 1 1 0 minus 1, sorry, 3 minus 1 2. So if you see this one, this is equal to this. So minus 2 1 3 minus 2 1 3, 1 0 minus 1 1 0 minus 1, 3 minus 1 2 3 minus 1 2. Then we say that this matrix is a symmetric matrix. So any matrix, if the matrix is equal to its transposition, then that matrix is a symmetric matrix. 0 1 matrix here is all the matrix will have zeros and ones, okay, and the 0 represent false and 1 represent true. For example, over here 1 0 0 0 1 0 0 0 1. Now here 0 means false and 1 means true. This is called binary matrix, okay. Now here there are two operations for 0 1 matrix, that is join and meet. Join is an or condition of true or false, and meet is an and condition of true or false. For example, over here, if you want to join these two, it means an or condition. You do or between these two, okay. 1 or 0 is 1, that is true or false is true. So 0 or 1 is 1, 1 or 0 is 1. Then 0 or 1 is 1, 1 or 1 is 1, 0 or 0 is 0. So 0 means false, 1 means true. If you do this one, for example, 0 false or false is false, okay. Meet, it means an and condition in which you check the and condition. For example, true, that is 1, and false, that is 0 is true, and false is false, so you write 0, okay. 0 and 1 is 0, 1 and 0 is 0, it is true and false. 0 and 1 is 0, 1 and 1, that is true and true, it is true, that is 1. 0 and 0 is again 0, false and false is false. So this is the join and meet of the two 0 1 matrices. Finally, we have the Boolean product of the 0 1 matrix. Now here in the Boolean product of the 0 1 matrix, okay, the same condition as we have seen the product of two matrices. The number of columns of the first matrix should be equal to the number of columns of the second matrix. Then you can multiply. While multiplying, for the addition you have to use or, and for the multiplication you have to use and. For example, if you see this one, so we are multiplying a and b, the Boolean product of a and b. So it is first 1 into 1, for into we use and, 1 into 1 plus first row first column, right? So 0 into 0, so 0 and 0. For into we use and, for plus we use or. So we are going to add these two by or. So if you solve this one, again first row second column is 1 and 1 or 0 and 1. Again first row third column 1 and 0, 0 or 0 and 1. And if you solve this one, you will get these values. For example, this one 1 and 1 is 1 or 0 and 0. So it is 1 or 0 is 1. So you go on solving this one, you reach the final matrix. This is called Boolean product. So this is all what we have in the session set operations and matrices. I hope this recording will be useful to you, and if you have any doubts during your studies or after you watch this video, please make a note of what is your doubt, and you can write to me on my university email on msuliman@arabou.edu.sa. And thank you for the watching. All the best for your coming midterm exams. Thank you.